Okay, this is another good set of conceptual questions about the relationship between the electric field and the electric potential and electric potential energy. So we have in our universe here a constant electric field. And we want to know what happens as we take a positive point charge and move it around in this field. Remember, the electric field is the negative gradient of the electric potential. So perpendicular lines here would be constant potential or equipotential curves, and the electric field points from higher to lower electric potential. So the potential is higher at B or at A than it is at B. So moving from A to B, we're going downhill. The electric field points from high to low potential, points downhill. Anything that moves through a constant electric field will be moving from one potential line to the next and so forth. So if you move in the same direction as E, then the change in potential is just negative E times the distance you move. Or if we think in terms of forces and energy, remember the relationship, that whole grid square I drew out. The relationship between F and E is the same as U and V. So force is related to energy in the same way that E, electric field, is related to V, electric potential. So the work required is just force times distance because we have a constant electric potential energy, or we have a constant electric field. So if I want to move from A to B, I'm moving in the same direction as my force is pointing. Force times distance would give me energy. Force is EQ. So the work that the electric field is doing to move a charge from A to B is just force, EQ, times distance, L. L is the distance, the length of this, each side of this square. If I want to move from D to C, same thing. I'm moving in the direction of the field. Then energy, the change in energy, is just E times Q, the force, times the distance. Or another way of saying all this is change in potential, change in V, is E times L. What if I want to move from A to D? Now I'm moving along an equal potential curve. My electric field is the same. I'm moving perpendicular to the electric field. There's no force that I'm moving with or against. To move from A to D is free. There's no energy requirement. Energy only happens when you move parallel to the electric field, because I'm on an equal potential curve here. What if I want to go along this path, A, D to C? That's the same thing I had to go from A to B, from D to C. To go from A to D is free, and then D to C. In fact, no matter what path I take, remember the electric field is a conservative electric field. Changes in energy are path independent. No matter how I move to go from A to C, I'm always going to have the same energy change. I could take my charge and move it all around for 17 years and then bring it over and place it at C. And the answer, the change, the amount of work the field does is EQL. Along path G, along path F, doesn't matter. If I'm moving from A to C, it's path independent. All that matters are the inputs, or the end points. What if I move backwards against the electric field from B to A? So I start here at B and move against the electric field. Well, now I have an angle of 180 degrees. Remember, work is force dotted with displacement. The dot product of anti-parallel vectors is -1. So that would be a negative change in energy or a negative amount of work.